Thank you for your interest in Vivado HLS, Xilinx's high-level synthesis solution which synthesizes C, C++, and System C functional specifications into Verilog and VHDL RTL architectures. We will illustrate the benefits of a C-based design methodology with the implementation of an image processing algorithm. The algorithm works on a color image, performing color transformation and then edge detection. The algorithm is written to test different color transformations before the edge detection is applied. This generates alternative output results. That is a typical scenario for initial design where the designer wants to fine-tune aspects of the algorithm. Vivado HLS offers built-in C simulation capabilities to help the designer with this fine-tuning. Here, we start a Vivado HLS debugging session of the image processing algorithm. This function call represents the design to be implemented in RTL. Inside this design specification, two function calls take care of the filter activities. And in the first filter, a loop takes care of the color transformation of all the pixels in the frame. The current configuration settings execute a color to sepia conversion. With the debugging capabilities accessible from within Vivado HLS, it is easy to get a good understanding of the execution of the design description. The timer shows the speed of the C simulation towards completion. The test bench successfully matched the output image to the reference image. This illustrates one of the benefits of C-based design, where algorithms can be verified quickly with comprehensive methods. Now that we're satisfied with the design specification, we can go ahead and synthesize it into RTL. For our demonstration, we want a physical clock at 75 MHz. The goal is to process 60 frames, or 55 million pixels, per second. The target is a Kintex 7 device. The first synthesis run typically establishes a baseline. The baseline creates a comprehensive report to see where the designer needs to provide directives to get the desired architecture. Vivado HLS shows extremely fast synthesis times where thousands of lines of C specification can be processed in just a few minutes. This, in turn, leads to an opportunity for design space exploration to really fine-tune the architecture, driven by performance, resource, and power metrics. The Verilog and VHDL RTL are now available as synthesis results, our very first architectural solution for the C specification. The corresponding report gives us an estimate of the power and area. Notice the current memory requirements for the algorithm, which at 139% utilization surpass the availability for our Kintex 7 target. And of course, there's also a summary of the performance metrics. The clock period of 9 nanoseconds gives us 110 MHz, so the physical clock of 75 MHz would be no problem. However, the latency of almost 52 million clock cycles would limit the frame rate to less than 2 frames per second. We will address this performance challenge with a new solution for the same C specification. We simply copy any and all constraints from our first solution. For this second solution, we would like to introduce some process parallelism by having the two filters of the design run in parallel. Vivado HLS makes this easy for us as it extracts the optimizable objects from a C specification. These are basically the functions, loops, and arrays. The top-level function calls the two filter functions. By default, Vivado HLS respects the sequential nature of processes described in C. We can force an architecture with parallel execution with a simple directive. One of the directives Vivado HLS provides at the functional level is the Dataflow Instruction. This does precisely what we want: create an architecture which allows processes to work independently and communicate information to each other over channels. We can also control those communication channels between the processes. Because the filters go through the pixels in the same order, we can simplify the channels between processes and turn them into small streaming FIFOs. Finally, we accelerate the individual functions by pipelining the loops. We have entered just a few directives through the GUI. However, this can also be programmed through the Tcl-based command language interface, which makes it even easier to do design space exploration. Now, we're ready for another synthesis run. Notice that the C-based design specification is untouched. The directives take the same functionality and create fundamentally different architectures for it. The report now shows a solution well within the range of the resources offered by the Kintex device. And the performance numbers indicate that the Dataflow can handle new frames about every 900,000 cycles. With a clock frequency of 75 MHz, this would allow for a speed of 81 frames per second. This brings us to the next steps. Verify that the RTL works with the original C-based test bench, and package the RTL for bitstream implementation. For this demonstration, we picked the System C architecture result and co-simulate it with the original test bench. Since the simulation now has bit-accurate and cycle-accurate RTL transactions for the design, the test is going to take a long time. This illustrates even stronger why designing and fine-tuning at the C level provides such a productivity gain. Many customers easily experience a 30 to 50% improvement in productivity because of the accelerated verification cycle during algorithm fine-tuning. Vivado HLS handles all the details to hook up the original test bench to the RTL design architecture, compiles and executes the mixed level design, managing the variety of data files required for this verification step. At this point, let's fast forward to the end of the RTL verification run. We can see that the RTL architecture created the correct result with the image produced in our simulation directory. Vivado HLS also measures the actual latency and reports the success of the RTL verification. Note the huge gap in time required for C-based simulation versus RTL-based simulation. For larger designs or test benches, RTL-based fine-tuning simply takes too long. We have an architecture that satisfies our physical constraints and is functionally correct. All that is left is to pass it on to the system integration environment. Xilinx has adopted the IP-exact standard to package IP and hand it over from one tool to another. Vivado HLS packages up the RTL architecture for integration with Vivado IP Integrator. In summary, Vivado HLS brings productivity to the table by accelerating the verification activities. The design space exploration and advanced HLS techniques create quality RTL architectures. And the integration for RTL verification and RTL packaging makes it easy to bolt the HLS methodology onto your existing design flow. Xilinx would like to once again thank you for your time.